All right, everyone, welcome. Today, we're diving into a really cool concept from differential equations. It's called eigenvalues and eigenfunctions. And this is where the math on the page really starts to come alive and describe the physical world around us. Everything from a simple guitar string all the way to quantum mechanics. So let's kick things off with a bit of a puzzle. You see, for a ton of problems in math and physics, there's this one answer that's always technically correct, but it tells you absolutely nothing useful. So that begs the question, why is the easiest answer so often the most useless one?
Okay, take a look at this differential equation. Now the solution, y equals 0, works perfectly. You can plug it in, and yep, 0 equals 0. But if this equation is supposed to describe, say, a vibrating string, then y equals 0 just means the string isn't moving. I mean, sure, that's true, but it's not exactly helpful, is it? We call this the trivial solution, and our real mission is to hunt for the non-trivial solutions, the ones that actually describe what the system is doing. And that's where our two main characters for today come onto the stage. First, we have eigenvalues. That's the Greek letter lambda. Think of these as the special secret keys that unlock those interesting non-trivial solutions. And the solutions they unlock, we call those eigenfunctions. The bottom line is, only very, very specific values of lambda will let us find a solution that isn't just 0.
So, how do we find these special lambda values? Well, we need a plan, a systematic approach. We're going to play detective and investigate 3 separate possibilities for our suspect, lambda. We'll check what happens when it's positive, what happens when it's exactly 0, and what happens when it's negative. This covers all our bases and is going to help us crack the case.
Let's open our first case file, what's known as the Dirichlet problem. Now in this scenario, we're looking at a system with fixed boundaries. The perfect mental image for this is a guitar string held down nice and tight at both ends. Okay, so here are the rules of the game for this first puzzle. We have our standard differential equation, but now we've added 2 really important rules or boundary conditions. The solution y has to be 0 at the very beginning at x equals 0, and it also has to be 0 at the very end at x equals L.
First up, we're going to investigate the case where lambda is positive. When it is, the general solution to our equation is this nice combination of sine and cosine waves. And that makes a ton of sense, right? This describes something that oscillates, which is exactly what a vibrating string does. All right, now let's apply our first rule. Y of 0 has to equal 0. So we plug in x equals 0 into our solution. Well, you know the sine of 0 is just 0, so that whole second term vanishes. And the cosine of 0, that's 1. So we're left with c1 equals 0. That forces our first constant to be 0. A really nice quick simplification. So look at that. Just by applying one of our rules, we've basically chopped our general solution in half. All we have left is the sine term. We're getting closer, but don't forget, we still have that second boundary condition to deal with, all the way at the other end, at x equals L. And this right here brings us to the absolute heart of the problem. When we apply our second rule, y of L equals 0, we get this equation. And the whole thing has to equal 0. Now sure, we could just set c2 to 0. But if we do that, our entire solution becomes 0. And we're right back where we started with that useless, trivial solution. No, we have to be more clever than that. So here's the crucial insight. If we refuse to make c2 0, then the other part of the equation has to be 0. The only way forward, the only way to get a non-trivial solution is to force the sine term itself to equal 0. And this is where the magic happens, where the puzzle just solves itself. For the sine of something to be 0, the something inside the parentheses has to be a multiple of pi. You know, like pi, 2 pi, 3 pi, and so on. So when we solve that for lambda, we make this amazing discovery. Lambda can't just be any positive number. It's restricted to this very specific, discrete set of values. And these are our eigenvalues. And for every single one of those special eigenvalues, we get a unique corresponding solution, an eigenfunction. These are the specific sine waves that perfectly fit our rules, starting at 0 and ending at 0, just like we wanted. Okay, time to open our second case file, the Neumann problem. Now, the rules are going to be different this time. Instead of the ends being fixed, we're solving for free boundaries. This time, it's the slope at each end that has to be 0, not the value itself. So the setup looks kind of similar. Same differential equation, but look closely at the boundary conditions. See that little prime symbol on the y? You know from calculus that means we're talking about the derivative, which is just the slope of the function.
So our new rule is that our solution has to be perfectly flat at both ends, at x equals 0 and x equals L.
With these new rules in place, let's actually go back and check out that case we kind of ignored before. What if lambda is 0? Well, if we set lambda to 0, our big, scary equation simplifies way down to just y double prime equals 0. And what does that mean? It just means our function has no acceleration, no curvature. Well, what's the only thing that has no curve? A simple straight line.
And check this out. When we apply our new boundary condition that the slope has to be 0, it forces the c in our line equation to become 0. But d can be anything it wants. This means that any constant solution, like y equals 5 or y equals 10, is a perfectly valid, non-trivial solution. So get this. For the Neumann problem, lambda equals 0 is an eigenvalue.
Now, when we investigate positive lambda again, a similar process happens, but because our rules are now all about the derivative, the logic kind of flips. This time, when we apply the boundary conditions, it's the sine term that gets eliminated, and the cosine functions are the ones that survive. The steps feel very familiar, but the family of solutions we get is totally different.
So let's put our findings side by side. The Dirichlet conditions, where the ends are fixed at 0, gave us sine waves and said no way to lambda being 0. But the Neumann conditions, with those flat ends, gave us cosine waves and allowed for that constant lambda equals 0 solution. This is so cool because it shows that just by changing the rules of the puzzle, you completely change the set of answers you're allowed to have.
So, why do we care? Why are we hunting for these special functions? I think this quote from the study guide gives us the perfect physical picture, standing waves on a string.
Here's what all that math actually means. Those eigenvalues we found, they're not just random numbers. They represent the natural frequencies that a system, like our guitar string, wants to vibrate at. Think of them as the specific musical notes that the string is capable of playing. And the eigenfunctions, those are the literal shapes of the vibrating string for each of those notes, the fundamental tone, the first harmonic, the second harmonic, and so on.
And that brings us right back to the beginning. The trivial solution, y equals 0, just means the string is sitting there, bored, not moving at all. But the eigenfunctions we worked so hard to find, those are all the interesting, dynamic ways it can move, the vibrations that actually create the beautiful sounds we can hear.
And I want to leave you with one last thought to chew on. If these are the natural preferred frequencies of a system, what do you think happens when you push that system from the outside at exactly one of its eigenfrequencies? This question right here hints at the incredibly powerful and sometimes incredibly destructive phenomenon of resonance, which explains everything from a singer shattering a glass with their voice to the famous collapse of the Tacoma Narrows Bridge.